Intermolecular dehydration of alcohols, okay? Dehydration equals a loss of water. Like if you're dehydrated, you lose water. It is an example of an elimination reaction. It's the one that we already talked about. HOH, remember, is H2O. So if we heat most alcohols with a strong acid, they're going to lose a water, and then they have that double bond there. This does follow Le Chatelier's principle. So if you need to make more of the alkene, you can, or if you need to make more of the water, you can, just by adding more of this. So dehydration is the reverse of hydration. And I want to show you this. This is intramolecular. Intramolecular is like an interstate, goes between the states. Well, intra is within the molecule. You can see here the water is pulled out from within the molecule. So here's another example of it. We learned Markovnikov's rule. The opposite of Markovnikov's rule is Zaitsev's rule. I actually didn't know it had a name. I always used to call it just reverse Markovnikov. It basically means if you're going to run through this process, if you're going to take out a water, you have to figure out which hydrogen you're going to take out. So I know I'm going to take out this OH. So my choice is, am I going to make the double bond here, or am I going to make the double bond there? Well, it's just like Markovnikov, the rich stay rich. So I'm going to remove this hydrogen. So I get a 2-butene instead of a 1-butene because I removed this hydrogen right here. It went away and I followed Markovnikov's rule. So like I said, it's called Zaitsev's rule, but it's just kind of a reverse Markovnikov rule. Just like Markovnikov, we say this is the major product and this one is the minor product. Okay, so this is now intermolecular dehydration of alcohols. If we take the temperature and we lower it from that 180 to about 140, and we use same acid that we were using before, this is now 2 alcohols together. We're going to remove water. So look, you've got an OH on one and an OH on the other. You're going to remove both OHs, but in order to make water, you only need H2O. So we don't need both the O's. So this, and this are going to go to making the water. And then what's left behind is going to make an ether. And the name of that is diethyl ether. Ether, as you can see up on the wall there, is ROR. So an intermolecular dehydration, which happens at a lower temperature, makes an ether. Not to be confused with intramolecular dehydration, which is again going to make that alkene. So one of them is predominant at 140 and one of them is predominant at 180 degrees Celsius. And ether, by the way, this is, you've got the ether bunny here. It's ROR. So you've got these functional groups over here on the outside. They can be big and long. They can be benzene groups. They can be rings. They can be chains. Ethers have really low boiling points as compared to alcohols because they're very much non-polar, or mostly non-polar. This oxygen right here, because of its extra electrons, does provide a little bit of polarity. So they can hydrogen bond, which we'll talk about in a second. They're colorless, they have pleasant odors, they have low boiling points, and they are highly flammable. So ethers cannot hydrogen bond with each other, but they can hydrogen bond with other OH compounds like water and alcohols. And that's, like I said, that's because of these electrons here provides this spot that's a little bit negative that's going to attach to this very much positive hydrogen. Ethers are relatively inert and they make excellent solvents because you see, ethers are, like I said, they're non-polar, but they've got this region that's kind of a little bit polar. Diethyl ether was the first pain reliever that they used. The problem is when they took it, it was a gas and they put it over people's faces. It did cause nausea, respiratory inflammation, and they used to overserve it and really hurt people. It's now since been replaced with other halogenated hydrocarbons. So if you're talking about anesthesiology, this would have been the first one. But from there, they got better at it. All right, oxidation reduction or redox. If you took AP chemistry, you had a really, really in-depth version of this. I'm going to go through the simple and organic version of it. Okay, so very quickly, redox is this, okay? Oxidation means that there is a loss of electrons. So in this case, the sodium is oxidized because the sodium will become positive. The sodium is going to lose its electrons and get a positive charge. The chlorine goes through what we call reduction because it gains electrons. Now, I like the word reduction because reduction to me means it gets reduced in a charge. This is what I learned in college was oil rig. I've also heard lion, Leo goes grr, or something like that. Leo the lion goes grr. But oxidation is a loss of electrons, reduction is a gain of electrons. So loss of electrons makes it more positive, whereas a gain of electrons is going to make it more negative. So in organic chemistry, we don't care about sodium and chlorine. Here's what we care about, carbon. A lot of times in Chem 1, kids will look at the periodic table and they'll see that carbon will have a plus or a -4 charge. But then as you go on with ionic bonding, you realize carbon doesn't really get involved in hydrogen bond. So the cool thing about carbon is that it can have an oxidation state all the way from a -4, -3, -2, -1, 0, 1, 2, 3, or 4. So sodium just has that +1 oxidation state. Carbon can have all sorts. So here's kind of the rules. A carbon to carbon bond does not alter the oxidation state because they have the same oxidation level. Every bond between C and H is going to decrease the oxidation state by 1. And every bond between carbon and something more electronegative, which is basically all other organic atoms here, specifically oxygen, nitrogen is what I'm interested in, will increase its oxidation state. So we can actually go through and count these. Here's my carbon. It's bonded 4 times to hydrogen and methane. That means that this carbon has a -1, -2, -3, -4 charge. What that means further is that carbon is pulling on electrons because it is more electronegative than hydrogen. So carbon gets way more than its fair share of electrons in methane. Now, moving along here, carbon is bonded to another carbon. That doesn't change it at all, but it's bonded to those 3 hydrogens, -1, -2, -3. This carbon is -2. This carbon has something interesting going on. If we look at this one right here. So we get -1, -2 from those hydrogens, but then the carbon is also bonded to an oxygen, which is now pulling the electrons towards it. So you have a +1 charge because the oxygen is pulling more. So you actually add it all together. You get the -2 that are coming from the 2 hydrogens, and you get the +1 that are coming from the oxygens, okay? And all together that gives carbon the oxidation state of a -1. Right here, This carbon is only bonded to other carbons, so it has an oxidation state of 0. So let's look at these ones. Again, you can practice. It's really as easy as counting. You've got this carbon here. It's bonded to 2 oxygens, or I'm sorry, it's bonded twice to 1 oxygen. That's twice as many electrons. So that's where it gets the +2 from. Those are from the oxygen bonds. And you have to count both of them. And then the -1 comes from the hydrogen. So that gets a +1 charge. This one gets a +2 charge because it's just got the oxygen. This one's got a +3 charge. And then you can see here, it's got a +4 charge. So if you work your way through all the examples I just gave, I gave an example of all the way from a -4 electronegativity or a -4 oxidation state all the way to a +4. Electronegativity up here shows you basically everything you need to know for organic chemistry. There's carbon. The only thing that carbon is more electronegative than is hydrogen. And then here's kind of everything else. And again, we're mostly looking at oxygen. All right, so let's take a look at this one. This is a good one to practice these oxidation states. I kind of just drew this up. So number 1 has a 1, 2, 3, 4, all pulling away from it. So it's got a -4 oxidation state. Oh, I'm sorry, a +4. Look at me, I messed up. Good thing. Didn't realize that was even under this. Sorry. So 1, 2, 3, 4, the electrons are pulling towards these oxygens, leaving the carbon positive here, a +4. This one, carbon is pulling towards it. And if sometimes people write arrows to show that, and then the oxygen is pulling towards it. So it has a -2 oxidation state. This one is one that we already did. That one is a -4 because carbon is pulling 4 times. Number 4 is right here. It's got 3 hydrogens and then it's attached to this carbon here, which doesn't change the oxidation state. So that one is a -3. This one is attached to a carbon. Don't be mistaken here that you think it's attached to a hydrogen there. It's not. So it's attached to 2 carbons, which don't matter. And then the oxygen is pulling towards it. So it gets a +2, the carbon does. Number 6 is attached to all carbons, easy peasy. That is going to be a 0 oxidation state. Number 7, it's pulling, oxygen's pulling twice. These are really good quiz questions to ask you. So it gets a +1 oxidation state. Number 8 is got a lot of oxygens pulling towards it. So it's got a +3 oxidation state. And then number 9 is right here. It's got these 2 hydrogens coming off of either side. And then it's got an oxygen, just like we had on the previous page, a -1 oxidation state. All right, do you guys have any questions? Good, thank you. All right, so oxidation of alcohols, just what it sounds like. We're going to take the carbon, like we were just talking about, and we're going to oxidate the carbon. This symbol right here is telling me that I'm getting involved with something that's going to change the oxidation of the carbon. That's going to be something that's going to be more negative, okay? So when we go through oxidation, we're going to lose this hydrogen, we're going to lose this hydrogen, and we're going to then double bond with the oxygen. So the carbon just became more negative. It went from this would have been a +1 to a -2 oxidation state. So this was an oxidation. Went from a -1 to, in this case, it says a +1, but we're not going to a +1. This one is going all the way to a +2. Oh no, there's a hydrogen here. Sorry, I thought that was an R. There we go. We are going to a +1. So those hydrogens were lost, okay? So these are easy. They follow the exact same pattern every single time. Remember when I told you primary, secondary, and tertiary alcohols would be important? This is why. A primary alcohol oxidates to an aldehyde. A secondary alcohol oxidates to a ketone. And this is pretty easy. This is because you're losing this hydrogen, you're losing this hydrogen. In this one, you'll lose this one, you'll lose this one. So you're left with a hydrogen and an R and an R and an R. So secondary alcohols oxidate to ketones, primary oxidate to aldehydes. Tertiary alcohols can't oxidate to anything. There is no oxidation because they don't have any other hydrogen available. So they're not going to oxidate at all. Now moving on, the aldehyde further is going to oxidate into a carboxylic acid, which we'll talk about, but you can see there, it can get even more oxidized. Here's one more kind of graphic of this, running through the greatest share of electrons to the least share of electrons. This is really good for organic chemistry because it shows us methane to methanol to formaldehyde, which is our aldehyde, and then to formic acid, which if you look up there is your carboxylic acid. So methane oxidizes to methanol, methanol oxidizes to formaldehyde or an aldehyde, and formaldehyde oxidizes to a carboxylic acid. And then this would be if you kept going. All right, so oxidation is the loss of hydrogen or the gain of oxygen. I've seen it written all different ways. You can think about as carbon is getting more negative or less negative or pulling or whatever. However it is you think about it, you can see here, we're either losing hydrogen atoms or you're gaining them back in. Here's the primary alcohol I showed you here. Here's the hydrogens that it's getting rid of. Secondary alcohol, there's the hydrogens it's getting rid of, and a tertiary alcohol, you don't have it. I do want to show you this while it's up here. This right here, this oxidizing agent, it's just written as like this. This means that it's usually something that's going to contain oxygen. Remember, when you have oxygen, you've got free electrons here. So it's something that's going to be a little bit negative, that's going to be pulling those hydrogens, which are positive. Thiols, really simple. If this is an alcohol, all right, a thiol, if you look on the periodic table, right below the O is an S. It's like you've replaced the O in the alcohol with an S. These are really, really stinky, and they're what's used in methane to make it smell so we don't explode. It's found in skunks and it's found in onions, and you can see them. They look like SH. They're just like the OH. They're polar, they're bent. They're just not as strong of a bond. Okay, so that's it.